Okay, so today we're going to be talking about nodal analysis and mesh analysis. So nodal analysis and mesh analysis are two very powerful circuit analysis techniques. In fact, they are so powerful and important that they should probably be considered some of the most important concepts in all of fundamental electronic circuits. So this video, it is really important for us as electrical engineers to master these two concepts, because then it will go on and allow us to analyze some really important application circuits that are actually used in like all of modern electronics, namely op amps and transistor circuits. So that's why these are extremely important. Plus, you can use them to analyze basically literally any linear circuit like that exists for the most part. So in this video, in order to teach both nodal and mesh analysis, we're just going to go over some detailed explanations of what they are and how they work. And then we also have some example problems that I'm going to work for us just to give us a really thorough understanding and breakdown of how these are. So it's a very straightforward video. It's probably going to take a while though. So just get comfortable and follow along, and then it should be as simple as that. But before we go any further though, please go ahead and drop a like on the video for me. It helps my channel out a ton. And subscribe if you like to stay up to date with any future videos. All right, with that out of the way, let's just jump right into it. The first place to start is a good introduction as to, we'll kind of talk about what nodal analysis and mesh analysis actually are. So nodal analysis and mesh analysis are circuit analysis techniques that are based off of not only Kirchhoff's laws, but Ohm's law as well. All right. So nodal analysis is based on Kirchhoff's current law, while mesh analysis is based off Kirchhoff's voltage law. If you don't know what Kirchhoff's laws are, like his current law and voltage law, then go ahead. I would suggest watching the chapter 2 video that I have already made in this series that covers the basic laws. I'll have that linked in the description below. So the first thing we're going to talk about is nodal analysis, and specifically nodal analysis that involves circuits using current sources, because it gets a little bit different when we use voltage sources, and so we'll explain that whenever I get there. So nodal analysis revolves around analyzing the voltage nodes of a circuit. Who would have thought, right? So real quickly, I just have going straight to it, we have the steps to determine node voltages. So step 0 is to select a reference node, which should be ground. Then step 2 is to label the other nodes. And then you can just label these in sequential order, V1, V2, V3, and so on and so forth for every node that is a non-reference node in the circuit. And then step 2 is to apply Kirchhoff's current law to each of the non-reference nodes, and then use Ohm's law to express branch currents in terms of node voltages. So where this is going to, all this leads to step 3, which is to solve the resulting system of equations, which is just like basic algebra. You can use a substitution method. You could also use linear algebra techniques, whichever you're most familiar with. So kind of a quick summary, what we're kind of leading to, like I said, we're ultimately trying to get to this system of equations right here that allow us to understand both the voltage drop across each element and then the current through each element in the entire circuit. All right, so there's just efficient methods to understand that. So real quick, let's just take a look at an example that I have right here. And so this example is actually going to be in variable form, so there's no actual numbers used for it. So I think it will be good for us to help understand the concepts. So let's just go through the steps one by one, and we'll kind of give a demonstration of what each step being executed looks like. So step 0 is select a reference node, which I have done right here, and I have labeled it the reference node. And so one way you can kind of look at these is like you might say this is a node right here and this is a node right here. Well, they all end up being connected to this same node right here. So these are all equivalent points. Like I could have put the dot right here, or I could have put the dot right there. And those would all be in the same reference node because they're all connected to ground. And you should be familiar with this symbol as a ground symbol. That is covered in chapter 2. So we have selected a reference node. Then step 1 says label the other non-reference node. So the non-reference node, of course, is any node that's not a reference node. And so that is going to be this one right here, which is labeled 1. And then this one right here, which is labeled 2. Then step 2 is to apply Kirchhoff's current law to each of the non-reference nodes. Now I've gone ahead also, and it's probably for your benefit to do this during step 2 as well, during step 1 as well, is label any of the currents. So here I've just labeled I1, then we have I3, I4, I2, and then we have I5 down here, right? So we have I3 coming out of this node, I3 going into this node, I2 coming out of this node, and then going into this node. So this just also will help us keep things organized and then help you understand like all of the different currents in the circuit, right? So if you look at all of these, like I1, 2, 3, 4, and 5, that's every current throughout the entire circuit right there. Okay, so now what we're going to do is, like I said, apply KCL to each of the non-reference nodes using Ohm's law. So looking at node 1, we see that I1 equals I2 plus I3 plus I4, right? Kirchhoff's current law. Hopefully this makes perfect sense to you right now. At node 2, we have I2 plus I3 equals I5. Again, should be very straightforward. We have I2 and I3 entering the node, I5 exiting the node. That's where we get that equation from. Okay, so now we want to take these two equations and use Ohm's law to express currents in terms of node voltages. Reference node is assumed to be 0 volts. You can rewrite Ohm's law. So this is a really important piece of information as well, is that you can rewrite Ohm's law. I equals V higher minus V lower over R. Another way to explain this or understand this is like we know that current flows from a point of higher potential to lower potential. And then we know that a voltage drop across an element or across just a voltage measurement in general is a differential measurement, meaning we measure between 2 points. And so what we're assuming is that the current is flowing from the higher point to the lower point. Okay, so rewriting these equations using Ohm's law, we'll have a quick example. So we have I4 equals V1 minus 0 over R1. So let's go up and look at I4. So we have I4 is equal to V1 minus 0. So where do we get those numbers from? So V1 comes from up here. We have node 1 right here. And then we have 0 volts down here. We have the reference node, right? So I4, which is flowing through this resistor. So we have current from V higher minus V lower divided by the resistance, okay? So V higher is V1 in this case. V lower is the reference node, which is assumed to be 0. So that's where the 0 comes from. And then divided by R1, that's Ohm's law. Okay, so that's the equation for I4 right there. So hopefully that makes sense. And then as we do more of these, hopefully it'll start to make more and more sense as we just start to see the pattern. Okay, so let's take a look at I3. Okay, so I3, as we know, is going through R2. And remember, so we're assuming that the current is flowing from a point of higher potential to a point of lower potential. So that would mean that the point of higher potential is node 1. The point of lower potential is node 2. So that means if we were to write this in terms of Ohm's law, just like it says, we would see V1 higher potential minus V2 lower potential divided by R2, which is the element that the current is flowing through. Let's take a look at I5 now. So we have I5, which is flowing through R3. And then we are again flowing from a point of higher potential, which is going to be V2 or node 2, to a point of lower potential, which is supposed to be our reference node, which is assumed to be 0 volts. So you can just replace the V reference node with 0, meaning when we convert this into Ohm's law, we have V2, which is node 2, divided by, or minus 0, divided by R3, which is the element that I5 is flowing through. So that is where we get that equation from right there. Okay, so we have V2 minus 0 divided by R3 is equal to I5. Okay, so hopefully that makes sense. Step 3 is to solve the resulting system of equations. So again, this is kind of just like a basic algebra. So we're using Kirchhoff's current law right here. So we have I1 equals I2. And we know I2 in this case is equal to this current source. There's no impeding element, so we just plug I2 directly in, plus V1 over R1. We just took out the 0 right there, plus V1 minus V2 over R2. And then we have this one plugged in, I2 plus V1 minus V2 over R2 equals V2 over R3. So we're just substituting wherever we have a variable that is known in terms of like voltage and resistance, then we just substitute it in right there. And that's where we get that from. And then what you would do is there are like several methods you can use to solve this system of equations. So it kind of makes sense to stop it here in terms of whenever we're doing just like variable notation, whenever we have real numbers, we'll actually solve for the real numbers, which is exactly what we're going to do now, right? So let's take a look at a real example with real numbers, okay? So boom, here we go. Here's our circuit that we're going to analyze. We're using the same exact node voltage method, and we have current sources as well. So step 0, select a reference node. Conveniently, boom, it's labeled for us. Reference node, here's ground, assumed to be 0 volts. Step 1, label the other non-reference nodes. So if you see, there are 2 other non-reference nodes conveniently labeled for us, 1 and 2, right here. Okay. So now we want to apply KCL to each of the non-reference nodes. So here also during step 1, you might want to label these currents, which I have done. We have I4 going into this node, I2 going into this node, I1 leaving, I5 leaving, and then we have I3 here leaving, and then I1, of course, entering. Okay, so this is the setup we have. The directionalities of these are somewhat arbitrary. Now I will say, at least for I2, it's rather arbitrary. But if it's going towards ground, always make the current flow to ground. But at the end of the day, the math will work out, and you'll get negative numbers if your current's pointed the quote unquote like wrong direction. So don't worry about like the directionality necessarily. Like it won't affect your answer if you do the math right. Okay, so applying KCL to each of the non-reference nodes, we get our Kirchhoff's current law equations. We have I1 equals I2 plus I3. Okay, so I1 equals I2 plus I3. Should be straightforward Kirchhoff's current law. Hopefully that makes a lot of sense. But now let's go ahead and plug in some numbers because we know that I1 equals 5 amps. So boom, we got a real number right here. Now we're cooking. Okay, 5 amps equals I2 plus I3. I'm getting really excited. At node 2, I2 plus I4 equals I1 plus I5. Again, Kirchhoff's current law. I2, I4 entering the node, I5, I1 exiting the node. Okay, again, we get some numbers we can play with, but this time, we've upped the ante. We have 2 numbers we can plug in. It's going crazy now. I2 plus 10 amps equals 5 amps plus I5. We almost have too many numbers now. It's going to become too easy to solve this system of equations. Okay, but before we can solve the system of equations, we have to use Ohm's law to express the currents in terms of node voltages. Remember, reference node is assumed to be 0 volts. Current flows from a form of higher potential to a lower potential. Okay, recall chapter 1 and how to measure voltage, because that's where I covered how to measure voltage. So hopefully that makes more sense. Okay, so we have, again, we're going to pull these 2 equations. 5 amps equals I2 plus I3. That's what this one is in terms of Ohm's law now. So I2 has been converted into V1 minus V2 over 4. So let's take a look at the I2 right here. So we have I2 right here, and it's flowing this way, or assuming this is to be higher potential, this is to be the lower potential, and then we're going through 4 ohms, okay? So that means V1 minus V2 divided by 4. That's where we get that from, okay? Now we have I3. What is I3? I3 is going from node 1 to the reference node, which is assumed to be 0 volts. So we have node 1 minus 0 divided by our resistance that the current is flowing through, which is 2 ohms. Boom. That's where you get that from. Okay. You do some algebraic hocus pocus, you get 20 equals V1 minus V2 plus 2V1. That's just the equation simplified for us. Okay. Next up, we have the same exact thing we're trying to do. So now we have I2 plus 10 amps equals 5 amps plus plus I5, right? So we're going to take, our job is now to take I2 and put it in terms of Ohm's law, and then I5, put it in terms of Ohm's law. Okay. So for I2, let's take a look at I2. I think we just covered I2 just a second. We actually just covered I2. So we already know why I2 is I2. However, but now we can still talk about I5. So I5, let's take a look at I5. So we're going from higher potential to lower potential. That means V2 is assumed to be the higher potential, and we're going to our reference node, which is assumed to be 0. So we have V2 minus 0 divided by 6 ohms. And just to be clear, I'm swapping, calling it node 2, and then like V2, which is just the voltage at node 2. Okay, so hopefully that was clear why we have it labeled as V2, but V2 is the voltage at node 2. Okay, so we have V2 minus 0 over 6. Boom, get our second equation right here, right? Simplified, so 60 plus V2 right? So step 3, solve the resulting system of equations. So remember, the resulting system of equations is 20 equals v1 minus v2 plus 2v1. 3v minus 3v2 plus 120 equals 60. Okay, so after you do all the math, then it just kind of works itself out. And you have v1 is equal to, like, here's the answers right here. So if you just do all the math, then that's what it comes out to do. Okay, so yeah, like that's pretty much how you do the node voltage method with current sources. Like I said, the main focus is just as long as you set up the problem correctly. The rest of the rest, I mean, the algebra and the math is relatively straightforward and simple. Hopefully that made a lot of sense. Like I said, if you have any questions about how to do this method using current sources, then drop a comment down below. So yeah, let's just keep chugging along. I think we're doing great. We just did node voltage method with current sources, but what happens if you put a voltage source right here? How does that change things? What do we do? Things get a little more complicated because there are actually 2 separate cases in which a voltage source can be applied. So let's take a look at those. Case 1 is when the voltage source is between a reference node and a non-reference node. So let's take a quick look right here. This is an example of case 1. We have a voltage source is between a reference node, which is 0 volts, and then a non-reference node, which is this one, right? So we're between this 0 volts and then V1. Okay, so that's case 1. What you do in that case is you set the voltage at the reference node equal to the voltage of the voltage source. So V1 would become equivalent to 10 volts in this case. And we're going to work out a specific example and how to do everything. So do not worry, okay? Case 2, and this is the more complicated case, is the voltage source is connected between 2 non-reference nodes. This creates a super node. Okay, so what you do at this super node is apply Kirchhoff's current law and Kirchhoff's voltage law to determine the node voltages. And we'll give an explanation because the super node kind of takes it's sort of like it has multiple characteristics simultaneously that we kind of have to demonstrate. I think is the best way to explain how it works. Yeah, we'll just keep going down and we'll explain how this whole thing works. Okay, so like I mentioned, the 10 volt voltage source is an example of case 1. So we said V1 equal to 10 volts. The 5 volt voltage source is an example of case 2, that means the reason this is an example of case 2 is because, like I said, the voltage source is connected between 2 non-reference nodes, meaning V2 and V3, right? This is not connected directly to ground, so we have to do extra steps, right? But don't worry, it's not that hard, okay? So the 5 volt voltage source is an example of case 2. Nodes 2 and 3 form a super node. We're going to do KCL on the super node. Okay, so what does KCL on the super node look like? That looks like, so we have I1 going into the super node, and then we have I4 going into the super node, right? So you see how we have like a circle around here. So what we're kind of do is we're kind of taking these 2 nodes, V3 and V2, and kind of squishing them together, right? Because what we're saying right here is that I1 plus I4, which is implying that they are both entering the same node. And then we equals I2 plus I3, which is implying they're both leaving the same node. So you want to treat these as the same exact node is kind of like what the trick is right here. Okay, so that means we have 2 currents entering the node and 2 currents exiting the node. And that is where you get your KCL equation right here. Okay, we kind of have to, when I talked about having multiple characteristics, what we have to do now is we have to use Ohm's law to write these in terms of voltage and resistance and stuff, right? So we have I1 is equal to V1 minus V2 over 2, which hopefully is pretty straightforward, right? And that should make perfect sense compared to the last example we just did. So now let's take a look at I4. The equation for I4 comes out to be V1 minus V3 over 4. So where we got those from is we have V1 right here, and then we have V3 right here, divided by 4. So hopefully that makes sense. Where again, it's just pretty normal Ohm's law. Higher potential, lower potential right here, resistance that the current's flowing through, to where you get 4. And then we have for I2, we have V2 minus 0 because our reference node is on the other end of this, divided by 8, which is the resistance of the resistance of the element that the current is flowing through. Okay, then we have I3, which is V3 minus 0 divided by 6. Again, very straightforward. Okay, so this is where we get our system. This is where we get, our equations for the super node. So next, we are going to do Kirchhoff's voltage law on the super node. And the way we do that is we're just going to follow the loop. So the loop that this element is in. So what I've just drawn an example of the loop, which is just the current path that the voltage source is going through, right? We just go from the positive, bring it around town, all the way to the negative. Okay, so Kirchhoff's voltage law, and in this case, I actually do this way, just because I wanted it to match this current source. Again, this is arbitrary, but as long as your math works out, it's okay. So for the purposes of this example, I've drawn the loop going this way. So we're going to go around the loop this way, right? So that means we have positive, we have a V3 to 0. So positive and negative. So that's V3, positive V3 right here. Then we have a negative V2 because we're going minus here, 2 plus here. And then we have a 5 volts, right? So that means we're going plus to minus right here. So this is what the Kirchhoff's voltage law equation looks like for the loop. So then we get V2 minus V3 equals 5 volts. Okay. So then all we do is just use a system of equations to find the node voltages. And it's pretty much as simple as that. Okay, so I want to show another example just to really cement the idea. This one has both current sources and voltage sources. So we'll go through and work the whole problem, and I'll show you the actual answer at the end. So step 1 is to apply Kirchhoff's current law to the supernode. And so that means we have 2 equals I1 plus I2 plus I7. So hopefully that should make sense there, where we have I2 going in the node. And then we have we have 2 amps going into the node. Then we have I1 leaving the node, I2 leaving the node, and then 7 amps leaving the node. And this is actually a really good example of, it doesn't really matter the directionality of your sources as long as that you do the math right. Okay, so converting I1 and I2 into Ohm's law, we get V1 minus 0 over 2. So that's pretty straightforward for I1, V1, 0. We've done this several times. Hopefully it makes sense. And then I2 is also the same. We have V2 minus 0 divided by 4 plus 7. So simplifying that down, is we get this equation right here. And then we want to apply Kirchhoff's voltage law to the loop. So we have just drawn, I think the reason why I drew this, and I forgot to mention this, is so going up here as well, it's just conventional to draw loops clockwise. That's the reason I did this. So that's just like a normal convention, right? That's what I did down here as well. So sorry if that was unclear. So yeah, so let's apply Kirchhoff's voltage law to the loop. So the loop is just the loop that has the voltage source in it, which is right here. So first up, we have a negative V1 because we're going minus to plus right here. So we're going from 0 volts to V1. So it's, of course, V1 is going to be negative. Then we have minus 2 volts because, again, we're going minus to plus. So that's going to be negative. And then we have a plus V2, which is because we're going from V2 to 0. So V2 is going to be positive, and that's going to equal 0 volts. So then we get this equation, V2 equals V1 plus 2. So this forms our system of equations. So we have this equation up here at the top, and then this one right here. Right, so that means we have these two. And then from the system of equations, we get negative 7.333 volts, and V2 equals negative 5.333 volts. And I actually think I went and simulated this one, so we'll take a look at it. But yeah, so it's interesting. We get negative numbers, which is totally possible. Like that's okay to do. It doesn't mean we did anything wrong, but just shows the reason we got quote unquote negative numbers is just because we made wrong assumptions. And because so what this means is, what a negative voltage means is that compared to the reference node, that means the reference node is like, what in this case, 7.333 volts higher than our reference node, right? Because if V1 is negative 7.333 and then this is 0, that's how that works, right? So I actually have a circuit simulation I want to show you, because also you're probably confused. What about this 10 ohm resistor up here? Like, what is that even doing? So we'll take a look at the and I even have a note on here. Final note: the 10 ohm resistor has no effect because it is connected across the supernode. Cool. So let's take a look. I even have some notes on the circuit simulation. So let's take a look at the circuit simulation. Okay, so here's the circuit that we just analyzed. And just to show you that we got the answers right, here's negative 7.333 volts and then negative 5.333 volts. So real quick, let's just go take a look. So here's the example circuit. So this one's 2 amps, that's 7 amps. We have I2, I1, and then we have our 2 volt voltage supply. And then like I said, we have the 10 ohm resistors. So the first note we have is current through I1 is backwards. So if you remember, we drew I1 and we just assumed it's going from in this direction. But then whenever we look at it, it's actually not. It's going backwards. And then I2 is the same thing as well. And I said, this is okay. This is perfectly okay, because as long, and like I said, this, as long as you set up your equations right and you do the math right, it doesn't matter, right? You'll just get negative numbers. Hopefully that reassures you. So the next note we have for this is the removal of the 10 ohm resistor does not affect the node voltages at V1 and V2. So again, we kind of solve for these node voltages, and you're like, well, what about the 10 ohm resistor? It in fact does nothing. So real quick, we'll just delete these two right here. So okay, so deleting them, like I said, it does nothing. The node voltages don't change at all. So I can put them back. Doesn't change anything. If you're wondering what it does change, pay attention to I measure the current through this that is being generated by this voltage source, and that's the only thing it changes. Right. So it goes from 5.6667 amps to 5.867 amps. So it's like 2 plus 200 milliamps, which makes sense because it's 2 volts divided by 10 ohms. So you're going to get 200 milliamps or 0.2 amps. So hopefully that like reassures you that we did everything right, and that it's like okay to get negative numbers, and that it's okay to make whatever assumptions you need to, as long as you set up your equations correctly and you do the math right, you're going to be just fine. Hopefully that helped a ton right there, because I mean, even after I did this equation and worked it out, it didn't really make as much sense to me until I looked at the simulation. So hopefully that makes perfect sense to you. So that covers everything that we wanted to for the node voltage method. So we covered, just a review, we covered both how to do it with current sources and voltage sources. So hopefully that makes a lot of sense for you. If you have any questions about the node voltage method, then please drop a comment down below. I'll be more than happy to answer it. Next up is going to be mesh analysis. And specifically, we're going to do mesh analysis with voltage sources, because if you guessed it, it actually changes up a little bit when we add a current source instead. Mesh analysis is another general procedure for analyzing circuits. A mesh is a loop that does not contain any other loop within it. Remember what a loop is from chapter 2. So in chapter 2, we covered like nodes, branches, and loops, and I even talked about nets. So hopefully it's familiar what a loop is. And then a mesh, like I said, just very tiny loop. The strategy is to use KVL to find unknown currents. Steps to determine mesh currents. So step 1 is identify all of the mesh currents and label them 1, 2, 3, and so on. Mesh currents are different from individual currents through elements. And we'll see that whenever we look at a circuit in a second. Then step 2 is to apply Kirchhoff's voltage law to each of the meshes. Use Ohm's law to express the voltages in terms of the mesh currents. So it's kind of like we're going backwards now. So we have the voltages and we're trying to express the voltages in terms of mesh currents. Step 3, solve the resulting system of equations. So just like the node voltage method, we're using all of these concepts, techniques to ultimately get us to a set of systems of equations where we just do algebra. Direction of the mesh current is arbitrary, convention is clockwise. So that's where I got that from. If you were wondering about why I was drawing my meshes clockwise, that was why. Let's take a look at this example now. So step 1 is identify all the mesh currents and label them 1, 2, 3, and so on. So in this circuit, there are actually only 2 meshes, which is this one right here and then this one right here. And then we also want to go ahead and label the element currents, just like in the previous method. You want all the element currents labeled on your circuit for just convenience, and so you can keep track of everything. So you have I1, I2, and I3 right here. Step 2 is apply Kirchhoff's voltage law to each of the mesh currents. So that means we're going to apply Kirchhoff's voltage law twice for each of these loops. So for mesh I1, we have negative V1 plus R1 I1, because we get V equals IR. So we have I1 R1 IR plus R3 times I1 minus I2. So the reason we're getting R3, so this is R3. So if we look at why was it I1 minus I2, so this is going to be going clockwise. That means this one's going to be going down. This one's going to be going up. Right, so that's why we have I1 minus I2, just because they're going in opposite directions. And that's going to be equal to 0. Kirchhoff's voltage law, set it equal to 0. So then that simplifies down to R1 plus R3 times I1 minus R3 times I2 equals V1. So next up, let's do mesh I2. So we have the same exact strategy we're going here. So we have R2, I2, right? R2, I2, that's where we get those two from. Then we have plus V2, and then we're bringing it around town. And then we have R2 plus R3, and then bringing it around town, we have R3 times I2 minus I1. So again, they're going in opposite directions. So they're going to be, that's why there's a minus sign right there, equal to 0, Kirchhoff's voltage law. So that simplifies down to that. So that this is our first equation right here. This is our second equation right here. Step 3 is solve the resulting system of equations. So we know that I1 is equal to mesh 1 because there's no other elements right here. We know that I2 is equal to I2 because again, there's no other elements here. And then we know that I3 is equal to I1 minus I2, which probably makes a lot of sense, I guess. Maybe it doesn't make as much sense because again, these are just algebraic terms. We're going to work on an example with real numbers just so we can see what we're talking about. So let's take a look at this example right here. So as you can see, there are only 2 meshes. So we've identified them. So identify all of the mesh currents and label them 1, 2, 3. So we have I1, I2. Then we also want to label the element currents as well. So we have I1, I2, I3. So we've identified both meshes, I1, I2, and then we have the element currents, big I1, big I2, and big I3. So now we're going to apply Kirchhoff's voltage law to each of the mesh currents. For mesh I1, we have 5 I1, V equals IR. Hopefully that makes sense. I1, there's 5 ohms right there, plus 10 times I1 minus I2. So we have the 10 ohm resistor in between the 2 meshes. I1, I2 are going in opposite directions, minus now 15 volts, so minus to plus. Hopefully that makes sense. Plus 10 volts right here also, because this is in the I1 loop, equals to 0. All right, so be careful, don't forget that, because I almost forgot that when I just explained it. So we have the minus 15 volts, so we're minus to plus here, and then we have the 10 volts right here, so plus 10 volts, plus to minus here, equals 0. That reduces down to 3I1 minus 2I2 equals 1. So this is our first equation for our system of equations. Next up, we're going to do mesh I2. So we have 6I2, which is this resistor right here. So we're just going around the mesh, like I mentioned, right? 6I2, there's 6 ohms I2, plus 4I2, 4 ohms I2, plus 10 I2 minus I1. So we have I2, I1 going in opposite directions, minus 10, which is the reason we have a minus 10 is because we're going minus to plus here, equals 0. So we have I1 equals 2I2 minus 1. System of equations right here. So that allows us to solve each mesh current. And then we know that each individual current is in terms of each mesh current. Hopefully that makes sense, meaning that big I1. So the reason we have big I1 is equal to 1 amp is because big I1, which is this, is equal to 5 little I1. Okay. And then big I2 is equal to 1 amp because big I2 is also equal to 5 little I1. Okay, so hopefully that makes sense. And then we have I3 equals 0 amps. Okay, so now we're going to talk about mesh analysis with current sources. Circuits containing current sources actually makes the mesh analysis easier. So yeehaw to that. Here's to making things easier on us, am I right? There are again 2 cases where the current source can be applied. The current source exists in only one mesh, and the current source exists between 2 meshes. And we'll talk about that in a second. So in the case 1, when the current source exists in only one mesh, set the mesh equal to the current source and solve the circuit like normal. Boom. Super simple. Here's an example where we have a current source is in only one mesh. So we set mesh I2 equal to negative 5 amps because we're going clockwise. And then relative to this clockwise assumption, 5 amps is supposed to be negative. Okay. So again, I'm going to repeat this. This should be a theme with nodal mesh analysis. It does not matter the directionality assumptions you make. As long as you set your equations up right, as long as you do the math right, you're going to be okay. I2, mesh I2 is equal to negative 5 amps. Okay. Then for mesh I1, we have negative 10 because we're assuming clockwise directionality. So we have negative 10 plus 4I1 plus 6I1 minus I2, mesh 2. And I1 is going down, I2 is going up through this resistor. So that's why they're an opposite. So that's why there's a minus right there, right? So then this is literally it. This is our system of equations right here. That's all we would need to solve that problem after that part. So then case 2 is a current source exists between 2 meshes. Create a super mesh by excluding the current source and any elements connected in series with it, A super mesh is when two meshes have a current source in common. So in this case, we would make a super mesh. Okay, and that actually looks like that. So I'll show you. We're gonna go step by step and explain how things are supposed to be done. Okay, so step one is identify all of the mesh currents and label them 1, 2, and 3. So we have two meshes again. So we have mesh I1, mesh I2. And then we have element currents, big I1, big I2, big I3. So big I1 is going here, big I2 is going out of this node, and then big I3 is going into this node. And you're probably wondering like, oh, wow, these are pointing the other way. I wonder which one of these is going to come out negative. So again, don't worry about the directionality that we assume. What I'll call step 1.5 is create the super mesh, exclude, and the way you do that, like I mentioned, is you exclude the current source and any elements in series with it. So we exclude the 6 amp current source and then this 2 ohm resistor right here. So we just have this wonderful, beautiful box. And then we have mesh, super mesh I1 and I2. And apply. Step 2 is then to apply Kirchhoff's voltage law to the super mesh. And then use Ohm's law to express the voltages in terms of mesh currents. So it's super mesh time. So what does Kirchhoff's voltage law look like on a super mesh? And so basically what you kind of do is you kind of just cut it in half and say, okay, in this portion of the circuit, we know that mesh I1 is going through the 20 volt and the 6 ohm resistor. And then we know mesh I2 is going through the 10 ohm and the 4 ohm resistors right here. So whenever we get around town to this circuit, this part of the circuit, we're going to just use I2. And then we're on this side of the circuit, we're going to use I1. And then that's why you exclude the resistor that's in the middle, because that way you just pretend it doesn't exist. And then, that's the easiest way to solve most problems, is just pretend they don't exist. So then we have, according to this, again, we're assuming clockwise flow when we get minus to plus, so we get a negative 20. And then we have 6 I1, because again, remember this 6 ohm resistor is on the I1 side of the circuit. So 6 ohms times I1 mesh. And then we have 10 I2, which is on the side of the I2 mesh. So hopefully we're following that. And then we have 4 I2, which again is on the side of the I2 mesh, equal to 0. So this is Kirchhoff's voltage law in terms of the mesh currents and the resistors that we get. Okay, so that simplifies down whenever you do the algebra, reduces down to 6 I1 plus 14 I2 equals to 20. Step 2.5 is apply Kirchhoff's current law where the two meshes intersect. So we know that mesh I2 equals mesh I1 plus 6. And where do we get that from? Okay, so again, assuming clockwise directionality, we assume that the mesh I1 is going into this node. So you can just imagine it going around into the node. And then we have mesh I2. Again, if we just assume clockwise directionality, we can assume this is leaving the node. Okay. And then also 6 amps is going into that node, right? So that's where we get that from. We get I2 plus I1 plus 6, or mesh I1 plus I2. So hopefully that makes sense. Like I said, we have mesh 1 going in, 6 amps going in, mesh I2 going out. So then step 3 is to solve the system of equations. So all of the work we have done to get to this point is we have this beautiful system of equations. We have mesh I2 equals mesh I1 plus 6. And then we have this equation that we pulled from up here, mesh 6 mesh I1 plus 14 mesh I2 equals 20. And then that results in I1 equals to negative 3.2 amps and I2 equals 2.8 amps. Remember how I said it's okay as long as you do the math right, things will come out negative, and they sure did, and that's okay. And so now I'm just going to end with some notes on the super mesh. So the first point is current source provides one of the constraint equations we need, Kirchhoff's current law. So hopefully you picked up on that pattern, is that the current source that we're using right here, this is where this comes from. This is one of the equations that we use to solve the problem ultimately, and that comes from the current source in Kirchhoff's current law. A super mesh has no current of its own. And I think what they mean by that is that it actually doesn't like source its own current, or that it doesn't like, you don't do a current analysis on the whole super mesh as a whole, right? If that makes sense. And then a super mesh requires the application of both Kirchhoff's voltage law and Kirchhoff's current law. So hopefully we did enough examples to where this was explained. Like this makes sense to you in your head. Like I said, if you have any questions or anything, leave a comment down below. I'll be more than happy to elaborate or even make follow-up videos to further explain these concepts, because they're extremely important. So I think it's really important to understand these before we go on. So I'll be happy to elaborate on them as much as necessary. Thank you so much if you made it to the very end of this video, and hopefully I will see you in the next one.